give sort of excellent. Give a little bit of a couple of sort of click OK here. Yes. Anchoring principles that were the kind of constraints that I take the mathematical realists of this talk to move in, and it's constraints that are very familiar from this Putnam paper, Models and Reality, that sort of a lot of the deterministic challenge is based on. And the first tenet that I take to be sort of constitutive of the type of mathematical realism at issue here, this idea of independence, that there in some way, shape, or form is a fact of the matter, whether a well-formed mathematical statement is true or false, and importantly, that this fact of the matter is independent of our cognitive architecture ability. So whether a statement is true or false has nothing to do with whether we are able to establish it or will ever be able to establish its truth or falsity. The second thing that might be a bit more robust is this idea that a good theory of truth for mathematical statements is like a good theory of truth for the natural sciences, some form of correspondence theory. So mathematical statements possess the truth value they possess because of the things talked about in them, not because they can be proven in our best overall theory or because it makes pragmatic sense to assume them, but just as in the sciences, it's because the things are the way they say they are if the statement is true, or they're not the way they are if the statement is false. And one of the reasons to have this theory also for mathematics is that it makes it much easier to explain why mathematics and science integrate so well. Otherwise, there's always this problem. How do we get different conceptions of truth work together so nicely in theories that involve mathematical aspects and non-mathematical aspects? If one theory of truth is a correspondence type, and the other one something else. What makes the whole thing a bit more interesting and a bit more difficult is this idea that if mathematical realism draws its main motivation from being continuous with some sort of scientific realism, it should also obey the type of restrictions and methodology that motivate scientific realism. That's what's sort of summarized under the principle of moderation here. So the idea that the implementation of principles of independence and correspondence must, in some sense, be naturalistically acceptable. Naturalism is, of course, a very broad church, so a lot of things fall under it. Here's a couple of things I want to exclude by using that label here. So in the explanation of how mathematical realism implements these tenets, we should not be allowed to make reference to scientifically unsupported entities or properties, like, for example, reference magnets, joint padding, perfect natural properties. So these kind of properties that do a lot of work in metaphysical theories, but that remain otherwise unexplained. We shouldn't be allowed to posit mysterious cognitive powers. And by that, I want to include non-recursive modes of inference, but also sort of this postulation of a Gödelian mathematical sense. So if Gödel says he can look straight into the set theoretic universe, I do believe that, but I don't think it's something we should be allowed to, in general, posit. I can't see the sets directly, unfortunately. And then the third part that's not really under the label of naturalism, but also something that I take to be essential for the position in this talk, namely that it's not an object realism. So I'm not worried about bumping into the number 17 on the street, but it's really a sort of mathematical structuralism that is at the core of this talk. So then, that's a mouthful, but the position at issue in this talk is a moderate mathematical structural realism and about a very restricted realm, the realm of arithmetic. Though if time permits, I'll say a little bit how it might be expanded to other important theories on structures later on. Now, given these principles, there is sort of a tension between the idea of independence, correspondence, and moderation, because if we adhere to moderation and sort of reflect on the nature of mathematical structures, we'll probably pretty quickly assume they're non-spatiotemporal, they don't interact directly with us. So the question is, how can we actually talk about these things? How can we make sure that our correspondence theory of truth works, that the statements we have about mathematics actually refer to the things we want them to refer to in order to have the truth value we think they should have? So how can the reference to mathematical terms, theories, or formal notions in general, really, anything that's abstract in the sense, be fixed without violating the constraint of moderation? And there's an extremely attractive meta-semantic way of going about here by just saying, well, the kind of axioms and rules we adopt, they constitute as implicit definitions. We don't baptize these things by pointing at them and slapping a label of them, but we develop theories just as the sciences do, and then we say, well, the kind of thing referred to by these theories is the kind of thing that makes true our descriptive content about them. So it's a very nice way of summarizing that by Gaussian grasp of the indefinables of geometry here, for example, consists precisely in the adoption of one set of truths involving them as opposed to another. So what this theory, geometry, refers to is just the thing that makes true our postulates about that thing. And similarly, this is something that will become important later on with regards to logical constants. So these are also assumed to be some sort of abstract mathematical objects. So a particular constant means that logical object, if any, which makes valid a specified set of sentences and or inferences involving. So here the shape of the implicit definition is a little bit different. We don't give an axiomatic characterization, but a rule-based presentation, the kind of thing that makes certain rules for example, conjunction truth preserving. Then we want to make sure that the truth condition and truth values of our mathematical statements are well formed and tractable. So we would like to have a certain determinacy of truth value. We would like to be assured that every well-formed arithmetical claim really is either determinately true or determinately false, depending on our ability to establish that, because if we don't have that guarantee, we don't really have any justification for saying that, well, independence false, right? It's okay to not be able to verify it, but we should have at least assurance that every statement does have the truth value one way or another. This is, of course, threatened by sort of the Mendelian incompleteness phenomena. So in first-order theories, not every arithmetical statement is decidable on the basis of a best feasible, i.e. a theory that adheres to moderation of arithmetic. So there will always be independent statement. How can we be sure that those statements actually do have truth value without even coming into the realm of what to decide whether these statements are true or false? How can we be certain that they are truth valuable at all? The second sort of determinacy is a determinacy of reference. We said that a statement of mathematics should be true or false in this correspondence sense if the things are as the statement says, or if they're not as the statement says. So arithmetical statements should possess their truth value in virtue of talking about a determinate structure, the natural number structure. Arithmetical vocabulary should mean aspects of this structure in some way. And of course, here we have some sort of Scholemian underdetermination. So we know that no matter how comprehensive any first-order theory of arithmetic is, we know this kind of theory will possess unintended non-standard models. So what allows us to say that we're referring to the standard model, the natural number structure. And this is then the first object-level formulation of the determinacy challenge for the moderate realist of this talk. So in light of the existence of non-standard models and undecidable sentences of arithmetic, how can successful reference to intended structures be achieved and determinate truth values of arithmetical statements be ensured, and this is the important part, by these naturalistically acceptable means, so without just primitively assuming it or involving metaphysical explanations that we exclude from the outset. And in a certain way, the answer is already sort of in the way the detracting phenomena are even phrased, right? They apply to first-order theories. So why don't just adopt a formalism that is stronger and allows us to exclude either the incompleteness of arithmetical theories or the existence of non-standard models? And there's plenty of candidates out there. So depending which kind of formalism you like, depending where you think the shortcoming of first-order logic in characterizing arithmetic lies, you might have your pick. If you think induction should really be talking about all properties and not just all definable properties, well, let's add a way of expressing that to the language by allowing second-order quantification, by really quantifying over all properties. And then we can prove that under the assumption of a certain semantics, this second-order version of Peano arithmetic, so the axioms of first-order Peano arithmetic with the induction scheme replaced by the second-order induction axiom, is indeed categorical, pins down a unique model. That is, we can be certain that we're talking about the standard model, or in the very least about unique model. Or you might think maybe the defect of first logic is somewhere else, and I'm kind of scared of second order logic. I want to remain with quantifying over first order objects. Then you might think, well, there's certain things we know to be true about the natural number line, but we're not able to express in first order language. In particular, that every number has only finite many predecessors, and we'll add a way, that would be natural number line, definitely not the standard one. we'll just add a way of expressing that to our language. So either by adding a finitely many or an infinitely many quantifier, and a sentence that allows us to say that for any object, it is not the case that that object is preceded by infinitely many other objects. And then this also makes it possible to prove that kernel arithmetic plus this additional statement is categorical, hence non-unique model excludes non-unique models. If you think that it is naturalistically acceptable, and I don't for the purposes of this talk, though I should say that there's been some recent arguments by Warren which try to show that the omega rule is naturalistically acceptable in certain situations. So this is not an option that's totally off the table. But if you are of the opinion that we can use it in a moderate way, then you might add the omega rule to your first order theory of arithmetic, and you'll get the result that you obtain a complete theory of arithmetic. I will not talk more about this option in this talk, but I do want to flag that that is one that is live out there. So it would be nice if it was all solved at this point, we finish up, grab a beer, enjoy the sun, and so on and so forth. But unfortunately, this is the place where the determinacy challenge seems to really only gather pace, because now we've adopted this richer formalism, and we might be asked, well, how can we be sure we have as firm a grasp of this richer formalism than we claim to have? So why do we know what the expression there's infinitely many, or there's finitely many, or for all properties actually refers to? So it seems we have moved the challenge away from the statement of the first order theory and into the meta theory of being able to ask about the notions we use to provide a categorical or complete characterization of arithmetic. That's a criticism that's already in the original Putnam paper. I'll just read the first quote. Some have proposed that second order formalizations are the solution, at least for mathematics, but the intended interpretation of the second order formalism, so the thing the second order quantifiers are supposed or intended to refer to, is not fixed by the use of formalism. The formalism itself admits of so-called Henkin, i.e. non-standard models, models in which the second order variables fail to range over the full powers of the universe of individual, and becomes, again, necessary to attribute to the mind special powers of grasping second order notion. So it's really not as if the original challenge disappeared, it just re-emerged at a different level and can ask it with the very same force. And this kind of issue has, by a couple of recent authors, turned into a general challenge to the very possibility of moderate mathematical realism. So it's turned into a challenge that tries to show that just in virtue of admitting this kind of reasoning, no position that is characterized by independence, correspondence, and moderation is actually a stable or feasible position. I want to sort of rehash two of these arguments here, because I do think they point at something important, but ultimately fall a little bit short. So the first one is by Warren and Waxman in a 2016 paper. They say, well, there's two sources of mathematical determinacy. If there's any, it can either come from the world, or it can come from practice. So either mathematical things are determinate because that's just the way the world is, or we are successful in our practice of pinning down these mathematical entities. Mathematical objects are non-spatial, temporal, abstract, and so on and so forth. So the determinacy in line with moderation cannot arise just from the object. That would be something like postulating reference magnets, as something that's naturalistically unacceptable. But on the other hand, given certain plausible assumptions about the nature of our cognition, mathematical determinacy also cannot arise from mathematical practice, because mathematical practice cannot encode non-recursive mathematical theories. Well, why not? Why can't we go to a second order formalism and use this categoricity proof? Well, because this strategy just pushes the question of determinacy back a step. An explanation is needed of how second order quantification could be determinate. And here we're in a familiar space of options. Either it's determinate because of the world, ruled out by the metaphysical constraint, or it's determinate in virtue of practice. But again, the constellation of second order logic is computationally unfeasible, so that's all ruled out, and the question just re-emerges and can't be resolved at the next level. Second argument is by Barton and Walsh in this wonderful and very large book, Philosophy and Model Theory, where they argue as follows. They use a formal fact, premise one, that no compact logic can succeed in categorically characterizing n. So whenever you have compact logic, you can always add non-standard elements to generate an unintended model. And then from that, they conclude that any logic that is capable of actually categorically characterizing natural numbers must be articulated semantically, because it can't be done on a recursive inferential basis. But here's the revenge challenge again: semantic articulation of logic stronger than first logic require recourse to notions, determinacy of which is much more endowed than that to the natural numbers itself, right? If I already need to refer to an omega sequence in order to characterize natural numbers as the omega sequence, I'm just presupposing what I want to show, or I even assume something stronger. So therefore, the mathematical realist as such is unable to resolve the issue of indeterminacy in a naturalistically acceptable way. And again, I think there is something to these arguments, and it's fruitful to sort of try to draw out where they, at least these two concrete ones, I think go wrong, then try to generate a stronger argument which subsumes them and see whether there's no way out of this more general argument. This is what I want to try to do now in the next part of the talk. And I think it's helpful to sort of first get a bit clearer on what type of determinacy it actually is that our mathematical realists sort of committed to on the basis of her assumptions. Because there's at least two ways to try to implement or formalize this, two desiderata of arithmetical determinacy. On the one hand, one might want to demand the determinacy of truth value, right? So the ability of a theory of arithmetic to be able to decide all sentences of the language, that is to either establish phi or the negation of phi, to be able to formulate a complete theory of arithmetic. The second one is to be referentially determinate, that is to formulate a categorical theory of arithmetic, that is a theory that has precisely after isomorphism one model. We're structuralist, right? So the isomorphism class is fine as the intended model here. And of course, if we have B, we sort of get a type of version of A. So if we have a categorical theory, then every sentence of the language will at least be semantically determinate. So only a sentence phi or its negation will follow from the theory for any sentence phi. So given referential determinacy, categoricity, we kind of get completeness in a particular way. We can't establish it, but that was never part and parcel of the sort of package of the mathematical realist, right? We just need a way to make sure that every statement is either true or false, totally regardless of whether we're actually able to establish its truth or falsity. So that seems to suffice to sort of meet the constraints of the mathematical realist. So something going forward that I want to adopt, and that I'll try to show that the other positions, at least in part, also adopt, is that for the realist, categoricity is actually the right kind of property. So that is the kind of thing we need and want to establish if we want to have a determinate theory of arithmetic and a position that has it to respect independence and correspondence. And with this distinction at hand, I think we can sort of show that at least in the way these arguments are stated now, they don't really establish their point yet, because they do conflate two different types of determinacy a theory of arithmetic could possess. Or if you look at the second premise, this kind of determinacy is determinacy as categoricity, right? Just that the world is such that it proposes that there's just one structure that is the natural numbers and that imprints on you in some way. The second one, however, referring to mathematical practice not being able to encode non-recursive theories, seems to take the determinacy standard of completeness. And that allows us to sort of ask, if we disambiguate this argument, right? If we replace the determinacy as categoricity with determinacy as completeness in the second premise, or the determinacy as categoricity with the determinacy as completeness in the third premise, whether there is a way to make that argument unsound. So we can ask, can determinacy as completeness arise from the world? And I think the answer should be no. It's very unclear how the world could be such that it just forces us to give us or to accept a complete arithmetic. I'm not sure that makes even conceptual sense. But we can ask whether determinacy as categoricity can arise from our practice, because there's nothing in this notion of determinacy as categoricity that forces the categorization of this object to be complete, right? It needs to be recursive, but it might very well be incomplete. So completeness is totally out of the picture. So at least in principle, there seems to be a way here. If we are able to provide a categorical, recursive, yet non-complete descriptions of either arithmetic or of notions that allow us to give a categorical characterization of arithmetic, then that challenge here might be avoided. Similarly for Button and Walsh's argument, because the critical premise here is this inference in the second premise that because no compact logic succeeds in categorically characterizing natural numbers, any logic capable of doing so must be articulated semantically. This would really only be the case if the goal of the moderate mathematical realist was a complete theory of arithmetic, right? Because the second premise just says, okay, it won't be incomplete, so we must make it semantic to obtain some sort of complete theory, or if the categorical characterization required a complete and exhaustive characterization of a notion. But again, A, determinacy as completeness is not the primary goal of the realist, at least of this thought, and there is, at least at this point, nothing that kind of actually forces B to be the case. So it's still a live option that we're able to provide a recursive, yet incomplete characterization of the types of notions that allow us to provide a categorical characterization of first-order arithmetic. And in fact, that's almost in fact, this leaves sort of two questions, two possibilities for a way out. We can, on the one hand, ask whether it is possible to give a recursive but incomplete yet categorical theory of arithmetic. And I think the answer should be no here. We will not, because they all will, depending on how you formalize them, it means non-standard models. But the second question, the second possible way out, is to try to answer the question whether it's possible to provide a recursive, incomplete, yet categorical characterization of a set of notions or of a notion that are sufficient for giving a categorical theory of arithmetic. So note, we're not attacking the determinacy challenge on the base level of the theory of arithmetic, but sort of on the meta level of trying to give a categorical characterization of the types of notions needed to give a categorical characterization of arithmetic. And I don't want to have you talk about it in the Q&A or over a beer later on. I don't want to sort of go fully into ways that you might pursue these, but there are at least two ways of doing so out there in literature. One is in a paper by Mursi and Topi from 2021, where they try to show that it is perfectly possible to naturalistically determine the full interpretation of the second order quantifiers. Once you have that, you of course get your categorical theory of arithmetic, and they argue strongly schematized as follows. So they adopt this realist assumption that categoricity is sufficient for determinacy for the realist. Then they quote the Dedekind fact that the categorical theory of arithmetic can be formulated full second order logic. And then they show that if we conceive of inference rules in a particular way, i.e. as open-ended, we will be able to determine the full semantics for second order logic. Why is that? Well, if inference rules are open-ended, that means they continue to apply no matter how the language under consideration is expanded. There's nothing that speaks against the in-principle nameability of any kind of property you can think of. And thus, if one of the acceptable interpretations would be a Henk interpretation that leaves out one of the properties, the rules for the quantifiers as open-ended would become unsound in a model in which it was suddenly possible to name this property. So therefore, open-endedness forces fullness, and then they need a fourth premise that they argue for, based on a dispositional theory of rule following, that the rules of inference are open-ended, and therefore that the moderate mathematical realist can determine to refer to the natural number structure. The second argument was one that I have a stake in, and that was originally conceptualized, formulated by Field in a 1994 paper. Again, it adopts the realist principle that categoricity is sufficient for determinacy, and uses the formal fact that a categorical theory can be formulated in verbal language plus the quantifier there's finitely or there's infinitely many. It was the second version in the beginning. And then it shows that in the context of language arithmetic, so where we have available a bunch of non-logical symbols, for example, for an ordering relation or addition or so, it is possible to uniquely determine the standard value of the quantifier there's infinitely many in a naturalistically acceptable way. And again, that gives us a determinate way to characterize notions that we can use to determinately refer to the natural number structure. Therefore, it seems that the challenge is interrupted at the level that Warren and Waxman and Button and Walsh pitched their skepticism to it. The question now is, and this is almost halfway through, but this is kind of where we're to get, is whether the challenge actually stops here, whether it's answered. Because I think the answer should clearly be no, because we can again just move the determinacy challenge one level backwards. Because after all, we're assuming that the second order quantifier, the quantifier that's infinitely many, has a particular meaning, but that meaning is, so the space of meanings for these expressions is specified by a particular background theory of meaning, and only relative to this background theory of meaning can we actually say that these expressions pick out a unique value in that, but there's no guarantee that the background theory itself possesses only one model, especially with something like ZFC. We know that it's underdetermined, and that underdetermination, of course, already transfers Staten. There's something Weston remarked in an article that was actually published before Putnam's paper. He says that, suppose that, as the alarmist maintains, there are two or more interpretations of the axiom of ZF, which are equally natural candidates for the intended interpretation, but which are not almost isomorphic. Then the all subsets condition is ambiguous, or maybe all subsets in one interpretation need not be all subsets in another. So the question really is at this point, how can the realist ensure that what the background theory thinks is infinite is in fact infinite? How can the realist that adopts this full second order logic ensure that what the background theory thinks is full is in fact full? So it's not in doubt now that this characterization a la Morrissey and Tropy picks out the full interpretation of the second order quantifiers. But what is in doubt is what that fullness ultimately amounts to, because there's multiple candidates for the interpretation of background theory, multiple ways that fullness can be spelled out. And so again, the problem for determinacy is only shifted one level back. Now at the theory of meaning for the expressions used, right, the categorical theory of arithmetic, and the question is, does that ever end? I hope it does, but first, I think it allows us to formulate the kind of argument that Button Walsh, Warren, and Waxman gave a piece of in maybe the more general form, namely as a regress argument to identify where the issue ultimately with that argument is. So this is sort of my attempt at trying to flesh out the structure of the determinacy challenge. So we start, as we start in the stock, at the bottom level, right? We observe that the first order theory of arithmetic admits non-standard models. And then we see that any strengthening of the theory of arithmetic needs to rely on a further first order background theory to meet moderation. It's not first order, we have something to explain. But then the first order background theory admits non-standard models, any strengthening of that background theory, and so on and so forth, and it never stops. So therefore the combination of independence, correspondence, and moderations is unstable. Moderate mathematical realism is unfeasible. And I think by looking at this argument as this type of regress argument, that might provide hopefully a way out, which I want to suggest now, because I think there's at least two ways to conceive of determinacy when it comes to the higher levels, and two ways to achieve determinacy kind of at the level of arithmetic. One is through the provision of a standard model, either of arithmetic or of set theory or of any stronger theory that fixes set theory, right? If at some point in this regress we can be sure to naturalistically provide a standard model, we know the challenge is solved and we'll translate all the way down, we have the standard model of arithmetic. But of course, given that theories become increasingly more powerful, arithmetic, set theory, and whatever comes afterwards, chances to do this naturalistically acceptable if we can't do it directly at the level of arithmetic are relatively low. So I think this strategy is ruled out. But I also don't think this is necessarily what is needed to save the realist position about arithmetic. This is the kind of theory we're still concerned with, not any of the other theories. Because all we need is that the theories higher in the regress or lower in the regress, depending where you start from, have sufficient determinacy for the types of notions you use further down to characterize arithmetic. And of course, we need to say what it means to have sufficient amounts of determinacy, but it needn't, and that's going to be the point in the next couple of slides, it needn't amount to the provision of a standard model. Of course, it would be sufficient to determine the standard model of ZFC to remove the meta-level indeterminacy, but it's not necessary as long as we have enough indeterminacy in the class of models that render our best theory of structures true, and they agree on the notions we need to characterize or provide a categorical theory of arithmetic. That should be sufficient to have resolved the determinacy challenge at the lowest level, the kind of level it was all about. Because again, it's not a realist position about every mathematical theory, because about arithmetic plus a little bit extra that will come to towards the end. And what it means to be sufficiently determinate, what has been suggested in the literature, what I want to take up here again, is that the notions, the relevant notion, need not in any case be characterized by the standard model, but they need to be absolute. Absoluteness is a nice notion that allows us to capture that, well, a partial characterization of a notion is robust enough such that the core meaning of that notion doesn't change under variations of the background. So this is nicely summarized by Van Anen in this quote where he says that intuitively speaking, a concept is absolute if its meaning is independent of the formalism used. So the formalism itself can be partial and inaccurate, but whatever it determines is invariant under uses of the formalism. So it doesn't really matter that we exactly pin down what that notion is. It only matters that we pin down enough or a type of notion such that there's no variations across formalism, such that the core meaning remains stable, no matter how we ultimately flesh out the background. As an example of some absolute and non-absolute notions, so in a particular class of models for ZFC, the transitive models, and I want to mention that this is like the importance of, small here, but I hope it's visible, the importance of these transitive models of set theory for the realist project as such was already emphasized in the field in this paper, where it says at the end, unless we assume the transitivity of models of set theory, there's really no way an answer to the determinacy challenge could even get started. But what is absolute across these transitive models is, for example, the predicate x is finite or x is infinite or x is equal to omega, or what is not absolute is the predicate x is unboundable or y is the power set of x. And of course, x infinite absolute is precisely the kind of thing we might want to go for in order to adopt the second solution, having the quantifier there's infinitely many. If we can show that no matter what the background theory, what the model of the background theory of structure ultimately amounts to, if they all agree on the meaning of the predicate is infinite, well then the quantifier, there are infinitely many, will get standard meaning, no matter how big the remaining underdeterminants in background theory, and therefore we can use it in the formulation of a categorical theory of arithmetic. But of course, what remains to be shown is that we somehow can, in a naturalistically acceptable way, pin down that the interpretation of the background theory, even if it doesn't have to be the standard model, it is in the very least transitive. And that problem can be reduced further. Much used lemma or theorem in set theory is the so-called Mostowski collapse. So as long as we can make sure that the interpretation of the epsilon relation is well-founded, we're able to find a unique transitive model that's isomorphic to this thing, since we're structuralist, epimorphism is sufficient for us to identify the two. So what is needed in light of this result is somehow a way to secure the well-foundedness of whatever interprets the epsilon relation in our background theory of structure, assuming it's some theory such as ZFC. And the way this might be done is by sort of reusing the strategy that was already used at the first level. There we use the quantifier there's infinitely many in the standard model, and here we can now use another of the members of the wonderful world generalized quantifier, the so-called well-foundedness quantifier, type 1-1 quantifier, which checks whether a particular relation is well-founded. We can characterize it by means of the very by the schema such that if phi is well-founded, then some version of the axiom of foundation follows. Adopting it as a rule is much different than adopting it simply as a sentence, i.e. as the axiom of foundations, because here this allows us to quantify over all those things, a lot more ways to bring it down. And one can show that with this axiom, while this characterization does not fully determine the standard meaning, it is enough to ensure that whenever this quantifier holds of a relation, and that relation is in fact well-founded. So by means of a notion characterized by this rule, we can ensure that a relation, E interpreting the epsilon relation, is indeed well-founded, guaranteeing the model to be transitive, guaranteeing to be the notion of x is infinite to be robust, being able to use them in the characterization of arithmetic, and therefore interrupting the regress and having determinacy of regress all the way down. So, briefly, so of course, a lot of assumptions that go into that, and just to emphasize those a little bit. So, if all this works out as hopefully it does, then the moderate mathematical realist can meet the determinism challenge in full, at least about arithmetic and a couple of other structures and theories that I'll mention in a second, as long as the meanings of logical notions are global. So as long as we're allowed to characterize those in terms of the semantic consequence relation, in terms of rules, if you will. And there's nothing I talk about here, but there's a lot that might be said about why this should be the case. And as long as the transitivity of the background theory can be guaranteed, which I think it can, if this fact is granted, and we'll use the well-founded as quantified. So despite the persistent undetermination, the regress can be interrupted. Are we fully done? Well, almost, but there's of course a couple of loose ends I want to at least briefly mention, because many parts of this project are still very much work in progress, so there's a lot more to be said. And I think sort of a hopefully helpful way to sort of picture what has been done so far and the way this determinacy has to be achieved is sort of reflect on the kind of statements that the mathematical realist wants to get a handle on, and statements of this kind, right? The truth of the statement in a particular structure. Now, the first question we asked, okay, it is rather indeterminate what the mathematical realist about arithmetic intends to talk to about. So the question was whether reference to the intended structure is determinate, and if the argument of the preceding goes through, then the answer should be yes, right? The mathematical realist is able to talk about the intended structure, the natural numbers. But of course, we can still ask, well, is this relation actually determinate, or does indeterminacy arise here? So is it possible that what it takes to be true in the natural number structure is not as robust as we thought it was, such that we might get deviation at this point again? And to be totally honest, I am not sure. There's sort of two results that pull in different directions. On the one hand, it can be shown that satisfaction of first order logic and the logic if they quantify this into many is absolute. For transitive models of set theory, though satisfaction in second order logic is not. But there's also this very nice result, a set of results by Hankins and Yang, where they show that two models of set theory can agree on the standard model of arithmetic, but they can disagree on their theories of arithmetic truth. So I haven't taken as careful a look at this paper as I should have. I assume it depends on the usage of non-transitive models of set theory. If so, then this kind of fact is not an issue for the realist. But even if not, even if it is the case that truth in a model is indeterminate, I don't think this is uncomfortable, but it's not a huge problem for the type of realist talked about here, because again, what was needed primarily was determinacy of reference, determinacy to the structure that we have given. But what fails at this point then is that we sort of get the completeness, the guarantee of the determinacy of truth value for free with the determinacy of the structure, right? Because now it can be the case that even though it's the same structure, it's not, they might disagree on which statements are true where. There is sort of a reverse challenge, which has to do with, well, what about this third component, right? We talked about the structure, we talked about the truth in the structure. What about the language itself? Is the language or the language that we use here, is that determined? Do we actually know what we're saying? Which was sort of formulated a bit floppily. And at first, there's sort of a positive result that the set of first order expressions and also second order expressions is absolute for transitive models of set theory. So we can't disagree here on the meaning, what we mean by our terms. But on the other hand, Colloquium and Weizsäcker have showed that arithmetic and syntax co-vary, right? So if we have a non-standard syntax that we're using, then the model of arithmetic we describe and characterize that it will also be non-standard, and we won't have a way of actually seeing that from within our theory of syntax, because that itself is standard. So if we're looking at the whole thing from the outside, we see that it's non-standard, but nothing internally would reveal that because they co-vary. And then this can be sort of turned or made into a sort of challenge for the type of defense I've made here, which is put to me by Balthasar. Well, if this is the case, right, if syntax, and I hope I'm not misconstruing you here, but if syntax and if arithmetic co-varies with one another, if I have one, then I kind of have a notion conception of the other. Well, why can't I just circumvent all this previous argument? Because as soon as I'm granted that what I say actually makes sense, i.e. a determined conception of syntax, well, it immediately follows from that I have a determined conception of arithmetic. That just follows on the very basis of having been granted by the skeptic that I have this determined conception of syntax. And I haven't formulated a fully general answer to it, but I think the answer to that should be like, well, it is true that the way we articulate the challenge was we started with some sort of language as opposed to syntax. So the whole base of that language we wouldn't be able to characterize the standard model of arithmetic. So by the kind of goal set by the moderate realist, it was not possible to achieve it on the basis they took as granted. If this argument comes here now, then the skeptic can just sort of move the argument one step back. Well, assuming that we have a determinate conception of syntax, we can ask, well, where does this determinate conception come from? Then I will provide a theory of syntax, first order theory to be acceptable. That theory has non-standard notations. And so what I can do is I can give a categorical theory of syntax, which will need to use full second order logic. And then the same question arises, well, how do I have a grasp of that? So it's really, hopefully, the same type of challenge, just in this case applied to syntax rather than arithmetic, which wouldn't be surprising, right? Because they co-vary with each other. So it's not actually a way out. And so my last few months of my life have hopefully not been wasted and some have been had much, much easier. Let me quickly finish up with some remarks on Putnam, because of course now the way to formulate the challenge and the problematization of the realist position owes a lot to this original paper, and I fully disagree still with the result of that paper, that type of external realism, so the type of realism by which we look from sort of a God's eye view onto the kinds of theories we have and how they determine one another, is unfeasible. There is no such viewpoint. We'll always start from within some sort of theory to give the characterization. This is from within is, of course, like super vague kind of locution that needs to be characterized further. What is very nice is that this perspective from within fits nicely with the naturalistic approach in general, at least as characterized by Medley, and the type of thing that wanted to be captured by the principle of moderation. But it also allows us to sort of say, okay, what should be the standards of success for the type of realist position at issue? And I think the standards of success here should be to develop a position that is, in Van Fransen's words, non-pragmatically self-refuting. So if I can't see from within my favored theory that what I want to reach can't be reached on the basis of the methods accepted by me, that has to be stability enough to say like, okay, I'm comfortable with this. Of course, it can always be wrong because there's no God's eye view. But again, that is just part and parcel of sort of the naturalistic realist project. And so importantly, the type of moderate realism that I'm trying to defend here is different from the type of internal realism Putnam ultimately settles on and that Button tries to develop. Because in order to escape the regress, Putnam and Button, they both sort of give up on correspondence at some stage. They say, okay, when we talk about models and we'll provide the meta theory of models, our notion of truth changes. It's no longer correspondence, but some sort of derivability in a second order theory of that kind. So of course that interrupts the regress, because now we have a standard to assess and we can use this all the way down, but it also takes away this idea that this can't be correspondence all the way down. So one of the sort of constituting realist principle. Moderate realism, on the other hand, rests sort of content with just internal stability. So it's not that by our own methods we can show that what we set out to achieve can't be achieved, but as long as there's no sort of contradiction in the pragmatic self-contradiction, no self-defeating principles by its own line, as long as we can't show by the methods we accept that we can't reach the goals we set ourselves, that's got to be fine. There's some sort of epistemic stability. Last slide. If one buys all of that, how far does an approach of this kind actually take one? Well, at least a little bit further, because we know that as soon as we have a determinate model of n, we also get determinate models of the integers and the rational numbers as well, by a set of old results. So every model of the rational numbers determines a unique model of the integers and the rationals. And we even get the intended model of finite set theory. But I think it's totally out of the question that we will get the standard model of ZSC. That is way too big. The question then is, of course, is that an issue for the type of realist pursued in this project? I don't think it is. Because if a realist wants to be naturalist, they'll probably want to be so on the basis of some sort of indispensability argument. The indispensability argument says we should be realists about the kinds of things that are useful to science, and that certainly includes the natural numbers, that certainly includes the real numbers, but it probably doesn't include the full hierarchy. And so the question left then is, okay, or at least one of the big questions left is, what about the real numbers? And I hope to have an answer for you in like a year's time or so, and I've had time to pursue my project on that. But until now, all I can say is, well, at least the methods adopted here don't work as directly for R, so it'll be interesting to see what comes out. Sorry for going longer than I was scheduled to, but thanks so much for listening and for being as well.